So if we're thinking about a particle, right, or a dollar isotope, let's say that it's element X, right? And so it's going to have some mass number, and it's going to have some proton count. And so there's 4 basic decays that it can go through that change its isotope, right? It can also do things like gamma radiation and things like that, but we're not going to worry about that so much. It can also go through fusion and fission processes, which is a different thing as well. But just remember that whenever you do any type of nuclear chemistry, the idea is that your mass number should be consistent for your reactants and your products. So if you sum up all of the mass number for your reactants, that should be equal to your mass number of all your products. Same thing for your atomic number or your atomic charge, is that those reactants and products should be equal to each other. And that includes negatives, right? So with things like electrons, then they have negative charge for their atomic number. And so you still want to just leave them as they are. You don't need to flip any signs, nothing like that. But you do want to make sure that those are balanced, right? So we have a couple of different kinds of decays. So we have our alpha particle. And does anyone remember what the mass charge is for the alpha particle?
4.
So the mass number is 4, and its atomic number?
2.
2. And it's basically like a helium atom. So you sometimes seen it written like that, or you can see it written with the alpha sign. Both of them are the same thing, right? So that's our alpha particle. We then have beta decay. And what's another name for a beta particle?
Electron.
An electron. So does an electron have any mass? Or like, does it have a mass number?
No, 0.
No. So it should be our 0, right? So it's actually got like a very, electrons do have mass, they're just really small, and so we won't see them in these equations. We do have our charge there, which is going to be a -1, because electrons are basically like the opposite of a proton. So their charge should cancel out the charge of a proton. So that's how I remember that. I have a -1 there. And so you can see it written like that with an electron, or you can see it written like that with the beta particle sign. From there, the other thing that we have is a positron. Now, what's the difference between a positron and a proton?
The positron is I want to say like positively charged electron, right?
It is a positively charged electron. And so sometimes what that looks like is it should have no mass, but it still has the +1. So you can also see it sometimes written like this as our beta particle. Right? And so the only difference between that and our proton is our proton is going to be a 1-1 with a P. Right? So while the symbols are there, they kind of help guide you along what their names are. You don't have to worry about the symbols as much. I'm more concerned with your mass number and your atomic number, right? So I'm worried more with these parts because we need those to be balanced in order for our dollar isotopes to be correctly identified. Right? I'm not going to make you write out what symbol it should be. So if you have it as a beta or you have it as an E, it doesn't really matter. Okay. And so the last one, I guess I might as well include it since we've written out everything else, is going to be our neutron. And so our neutron should be 1-0 neutron. So it still has a mass number, but it doesn't have any atomic charge. So when we think about our 4 types of decay, a lot of what's going on is told through their name. Right? So if we go through alpha decay, what do you think is happening in alpha decay?
What?
Mm-hmm.
I'm not sure. I'm not sure how to word it.
What particle is going to be involved in alpha decay?
The alpha particle.
Alpha particle. And are we going to gain it or are we going to lose it?
You're losing it.
Yep. So alpha particle is lost. And if we do beta decay, what do you think is involved in that?
Electrons.
So it's our electrons or our beta particle. And are we gaining it or losing it?
You're losing it.
Lost, right? What's another decay? Or not decay, but what's another radioactive process that we go through?
Gamma.
So we have gamma, right? And so you can have a gamma emission. And so this is losing a gamma ray. But does a gamma ray change our mass number or our atomic number?
No.
No. So what is a gamma ray doing?
Adding energy or
Right.
losing energy?
Losing energy. We're going to release gamma emissions, right? So we're going to lose energy. And so we normally see this if we have something that's high energy going to a lower energy. So sometimes when it decays, it might have become an excited isotope, right? And so then we can lose some of that extra energy that way. We also see it in fission processes or fusion processes when some of that mass defect is getting converted over. But when we think about daughter isotopes and coming from parent isotopes, this one's not really involved that much because it doesn't really change their mass numbers, right? It's just changing their energy associated with it. What other ones do we have? So we have alpha decay, beta decay. What about this particle? What do we do with that?
With the positive, I didn't see which one you marked.
The positron one.
Positron decay.
It's similar. It's called positron emission, but it's the same as positron decay, right? We lose a positron. And it's not that these other things can't happen in reverse. It's not that we can't add an alpha particle, we can't add a beta particle, but these are just common decay processes. And so these are kind of like the big four of what things can kind of go through, right? And then the last one is going to be called electron capture. And so do you think we're losing an electron or gaining an electron if we're calling it electron capture?
Gaining.
Gain. Now, for this nuclear chemistry, we're kind of focusing on the nucleus, right? So electron capture isn't like us just turning into an anion, right? It's not just an electron coming into the atom, it's an electron coming into the nucleus of the atom, right? And that's why our atomic symbol can change, is that it's not just getting associated with the atom, it's getting associated with the nucleus of the atom. And so using the name, you can kind of piece together what has happened. So if we want to take this unknown one here and we want to do something like electron capture, when we write that, we're going to get our M, our Z, and our X, and then we're going to add to that an electron. So what should our product be? Does our mass number need to change?
No.
No, it's
No.
just your top atomic number.
Right? It's just the atomic number. And so we're basically going to take that Z and we're going to add 1 to it. Oh, sorry, not add 1 to it. We're going to subtract 1 from it. Right? Because if we add up this side, Z plus or minus 1, then we're going to get the same atomic number on our products as we get from our reactants. And so that's what I would recommend when you're going through them, is use the name, the name of the process to kind of break down what's happening, right? Because if they, as long as you know your particles, so as long as you know these down here, then it doesn't matter what they tell you, you can be able to piece together whether it should be a reactant or a product. And then you can piece together what your daughter isotope should be.
Sounds good.
All right. So we're going to do one example of that. We're going to take something like, 106 Sg, and we're going to do a beta decay. And so I want you to go ahead and write out that full process there, right? So I want you to fill in the atomic number for Sg, and then we want to fill in our two particles that we should have on the right-hand side as well. Oh, sorry, this shouldn't be 106. I have that flipped. This should be 260. Because down here, this should be 106. And so if we're doing a beta decay, we should be losing a beta particle, which is an electron. And so what do we know about our daughter isotope? What should its mass number be?
105.
Sorry, mass number.
260, so
260. Now, if we make the atomic number 105, what element would that become?
dubnium.
Dubnium, right? But if we add these up, right, 105 plus a minus 1, is that going to be equal to 106?
Then you got to do 107. So that adds
Right.
up.
Because if we release a beta particle, what's happening is we're basically turning a neutron into a proton. So this is like the most common mistake that I see on them, is that we get in this habit that we think it should be 106 minus 1, and so we get 105. But in reality, us releasing an electron doesn't decrease our proton count, it actually increases it, and we should be becoming bohrium. Because this should become 107 plus a minus 1 to get to 106. Do you guys have any questions on that?
No.
Okay. Do you guys want to see another one, or do you guys want to move on to a different topic? Or we can also do half-lives.
I'm okay to move on to a different topic.
Okay.
I can just shoot.
What was that? Okay. So what other topics would you guys like to go through? There we go. All right. Now we're cooking. So we know that our thing is made up of just carbon, hydrogen, and oxygen. So we should have 40.0 grams of carbon, 6.7 grams of hydrogen, and that should be the rest is oxygen. So this becomes 53.3 grams of oxygen. Now I'm going to divide them by their molar masses. Because that would give me my moles. And so when we divide each of these by 3.33, we get a 1, a 2, and a 1. So our empirical formula is CH2O. All right. Now, from there, they want us to go ahead and we're doing a titration. Now, with that titration, it's saying that 1 gram is dissolved and titrated with 0.300 molarity NaOH. And so we want to find its molar mass. So from here, we have 30.00 milliliters of 0.300 mole per liter NaOH. And we know that this is a 1-to-1 ratio because we were told that we have an unknown monoproduct acid. So it should be a 1-to-1 ratio. And so this is going to tell us our moles of our acid. I need to divide by 1,000. So this becomes 0.0111 moles of our acid. Do you guys have any questions about that? All right, so if we want to find the molar mass, we take the 1.00 grams, divide it by our number of moles, and we get 90.09 grams per mole. So that's our first part. So that's up to a B, and none of that we have to do any of our like ice tables, anything along those lines, right? Those are just pure titration ones. But when we're looking at this next one, so when we're looking for the pH during the titration, we need to figure out kind of what's been going on into in our process. So we know that this pH is 3.43, and we've added in 10.0 milliliters of our NaOH. So if we think about this scenario, we've taken basically a weak acid, so we should start over here. And we've started to titrate it with our NaOH, and so our titration curve is going to look something like that. And so we know that our endpoint is at 37 milliliters. So when we're at this 10 milliliters, are we at the endpoint? Are we before it or are we after it?
Before it.
Before it. So in that situation, if we want to estimate our pH, how are we going to estimate it? What kind of solution would we have in this region? Is it just weak acid? Is it just strong acid? Is it just weak base? Is it just strong base? Or is it a buffer?
It would just be weak acid, right?
All right. So if we've added in any NaOH, it's not just a weak acid. All right. So when we first start off, this initial point, this is a weak acid only. And its pH will be found just from Ka and its concentration, right? That's where we can do an ice table and we can figure out its pH. But once we move out past that point, we're moving from being just a weak acid into being a buffer. And that's because while we have some of the weak acid still together, because we haven't neutralized all of it, we also have some of it once it's been deprotonated. Once we've added in that strong base, it's taken away that proton. So if we have a buffer, what equation should spring to mind?
Henderson-Hasselbalch.
The Henderson-Hasselbalch equation, right? And that is that we have our pH is equal to our pKa plus the log of A minus over HA. I'm going to get rid of this part. So this shows up often with titrations, and so you just want to make sure that you're paying attention to where in your titration are you. So that way you're going to be able to most quickly find your pHs because you're taking into account the actual situation going on. right? Other than that, right? So basically, at the equivalence point, you can neutralize your solution, and then you can see whether you should be a little bit on the acidic side or the basic side, depending on which one was strong and weak. So if you had a strong acid and a weak base, then you would be a little bit on the acidic side. If you have a weak acid and a strong base, you should be a little bit on the basic side. And if you're a strong acid, strong base, you should be neutral, right? So that's what's happening at equivalence point. Before that, you're going to have your buffers. And then before that, then you're starting off with just your starting material for your pH. After equivalence point, then you're just using your strong acid or your strong base to determine your pH. And we'll kind of get into that on this next section. So if we're looking for our pKa here, we're looking for this section. So we know the pH is 3.43. We don't know our pKa. Now, do we know how much A minus and how much HA we should have?
Yes, from, what is it, B?
From B. So we do know how much HA we might have started with, right? But what ratio, what value should I put in for my A minus and my HA? What do you guys think? So let's say that this, our molarity for, well,
Should it be the moles that we found earlier?
so if we put those moles in and we divide it by the 50 milliliters, so we found that we had 0.0011. Sorry, too many zeros there. 0.0111 moles. And we divide it by 50 milliliters. We could put that in as its HA. But there's a problem. Well, that would be our starting amount of our acid. Now, is all of that acid still there? Is that entire concentration still present in the situation that we're measuring?
No.
No. So how much of it has turned over? So there's a couple ways you can do that. You can go through the math and you can figure out how many moles of NaOH this is, and then convert them, right? So then you would change this concentration here based on how many moles of NaOH you've added. So you have to subtract those moles of acid, find its new volume. You can find them that way. But there's actually an easier way to kind of think of them. How many milliliters of that sodium hydroxide do we need to titrate it? For it to come to an equivalence point, how many milliliters of that sodium hydroxide did we need?
37 milliliters.
37. So if you wanted to think about it, we're kind of like our base is 10/37ths of the way there. And our acid has 27 of the 37 still left over. So they're kind of all scaled that this is basically 10/37 times whatever concentration that we started. And this is 27/37 times whatever concentration that we started with. And so these are going to cancel out, and we'll be left over with this, the ratio of 10/27. All right, so we don't have to do all of that fancy math. We can just use how close or how far we are from our equivalence point to give us an idea. So we can use that here. Do you guys kind of get how I made that shortcut?
Yeah, I see it.
Okay. So now we just need to plug in for our pK, or to find for our pKa. So we have 10 to the 3.43 times 27 divided by 10. or sorry, not this. So this should be 3.43 minus the log of 10 divided by 27. So this becomes a minus a negative 0.431. And so our pKa becomes 3.86. Do you guys have any questions on that part?
Nope.
Yeah, could you explain again how you got 10 over 27?
Sure. So if this was me doing my titration, right? 37 is when we get to our equivalence point, and 0 is kind of like when we started. So if we wanted to think about this in terms of our acidic version and our base version, when we have 0 of our NaOH, we kind of have 37 of our acid. When I put in 37 milliliters of my NaOH, I'll have none of that acid left, right? It should have all turned over. So the idea is that if this is our milliliters that we need, however far along we are, that tells us the fraction that should be either turned over into our X minus or left over as our HX. So if we get to our 10 mils, that means out of that entire 37 milliliters of our HX, 27 is still left over. We still need our NaOH in order to move that over. And 10 of it has moved over to become the base version. So it's kind of like looking at it in the terms of a percentage. You could go through and you can really turn it into moles of your HX and then moles of your base version and divide it by the new volumes to get them into concentrations. But all of that kind of ends up being the same. They keep that same ratio. If you wanted to see kind of what that looks like, it would be kind of like our base is, need some more space here. So a 10/37 of the way over to our endpoint, which we would multiply by the concentration of our HA, and that would be equal to our concentration of our A minus. And we're 27 of the 37th way there for our concentration of our HA, and that would be equal to how much HA is present. And this could be initial, and this could be initial. And you see how this 37 is both on the top and the bottom? We can end up just canceling those out. Does that make sense now?
Yeah, thank you.
Okay. So we found our pKa now. So we have this as 3.86 for a pKa. And now we can move on to the next part. So we have this, a different monoprotic acid. Now it's got the same molar mass as ours. So if we put in, if we do the same conditions, how many milliliters will it take to be titrated? If you have the same molar mass, you put the same amount of material in, they're both monoprotic acids. How many milliliters of that NaOH will it take? What do you guys think?
Would it still be 37 milliliters?
It would still be 37 milliliters because if we have 1 gram, and if they have the same molar mass, if we want to turn those into moles, that's still our 90.0 grams to 1 mole. So since they have the same molar mass, we're still going to get the same number of moles. And since they're both monoprotic acids, they'll both take the same amount of NaOH to get there. So when we put in this 40 milliliters, are we before the endpoint or after the endpoint?
After at that point.
After the endpoint. So if we're after the endpoint, can we use the buffer equation anymore?
You'd still be able to, right?
Well, when we do the buffer, it means that we need to have some concentration of the A minus and some concentration of our weak acid there. Once we get past the endpoint, do we have any more of this HA still together?
No.
No, all of that has gone. So we actually can't use the buffer because this is gone. There's no more HA. So the only thing that we have is kind of A minus and hydroxide. Now, we could look at finding the KB, right? Because we have a new buffer of our weak base and it's hydroxide, and then we could go from there to find the Ka, right? But it's not really that easy to do. In reality, once we pass the endpoint, what is going to dictate our pH? So if you think about your titration curve, in the beginning, our weak acid is really important. It buffers, and then it hits equivalence point. And so in this region up here, what's giving us our pH?
It would be all the OH that's left, right?
All the OH. So it's really just looking at that sodium hydroxide that's left over. So we know that we have 3.00 milliliters of our sodium hydroxide left over. It's got a concentration of 0.300 moles. And we know now that this whole solution has a volume of 90 milliliters. So we can figure out our concentration of our hydroxide by taking that 3 times 0.3 divided by 90. And then we can take the negative log of it to find our pOH. And so what should its pH be at 25 degrees Celsius? We know the pOH is 2. What should its pH be?
12.
12. And so one of the things that I would recommend is, I can't tell you how often I get 2 reported as your pH, is when you think about this, do one final check when you turn in your answers, right? If we put in too much base, should our pH be acidic or basic?
Basic.
Basic. So is a pH of 2 acidic or basic?
Acidic.
Acidic. And so that's one way to double check, so that way you won't make that small mistake of forgetting to turn it into pH and only reporting out your pOH. Okay. Do you guys have any questions about that first part before we get on to part D? Okay. Now, for part D, It's actually a really interesting one. It wouldn't be something that I would actually ask you guys for your final, but it does kind of involve a little bit of organic chemistry and kind of making you remember some stuff, right? So if we shine a light at this acid and it rotates the plane, it tells us something about that molecule. Do you guys remember what's related to us rotating light? There's a term for that if we rotate light.
Yeah,
Some molecules don't rotate light. Some will rotate them left. Some will rotate them right. So there's a term that's related with that. It's called chirality, right? So if you rotate light, you're going to be chiral. Right? Now, for an organic molecule, that means that if we are chiral, what does it tell us about that carbon? If we're looking for a chiral carbon, what does that carbon need to be do or need to do?
It needs to connect to 4 different things.
It needs to connect to 4 different things. Now, from there, there's a lot of things that you could kind of piece together. Is we know that our molar mass is 90 grams per mole, and we know the empirical formula up there, which has a molar mass of 12 plus 2 plus 16 of 30. So we know that its molecular formula is C3H6O3. We know that we need a carbon attached to different things, and we know that it's acidic, which generally means that we have a carboxylic acid here. So this means that this carbon needs to be connected to at least one other carbon. And we have 5 more hydrogens and 1 more oxygen kind of left over. Right? Now, this carbon here, the carboxylic acid one, can't be chiral because it only has 3 groups. So that means that it has to be either this one or this one that's going to be our chiral center. Now, the one at the very end can almost never be the chiral center because it's got to be connected to a lot of hydrogens because it's at the end. And so that's why we're going to make this one our chiral center. And so if it needs to be attached to 4 other groups, it kind of means that this needs to be an alcohol, this one needs to be an H, and this one needs to be CH3. Now, I probably wouldn't expect you to be able to get all those pieces together, but you could have, right? And I think that's kind of the neat part about this is that there's enough information there that you could backtrack it all the way out and you would end up with just this structure because that was all that you could make. But more importantly, I just wanted to make sure that we reviewed what it meant to be chiral or not. So that way you guys have that. And so just remember that chiral things rotate the light. Achiral ones do not rotate the light because their mirror images are the same. Do you guys have any questions on that?
I'm good.
Okay. Then let's look at this one. This one is talking a little bit about thermodynamics. And so we're going to use that to kind of practice our delta G's and our K's. So this process is called dimerization. It's when we take 2 of the same molecule and we turn them into 1, right? So making that dimer out of it, 2 of them. And so they want us to find the delta H for this reaction, the delta S for this reaction, and the delta G. So all of them kind of solve the same way. And what should that equation look like if we want to find the delta H for that reaction?
Isn't it like just products minus reactions?
products minus reactants. The only difference with these is we have to make sure that we scale them based on how many times we need it. So in this case, our product should be our N2O4. So for delta H of our reaction, that becomes 11.1 minus 2 times 33.2. Our delta S is 304.4 minus 2 times 240.1. And then once we have those, we can use that to plug in for our delta G. Do you guys have any questions on that part?
I'm good.
All right, so it's pretty straightforward. 11.1 minus 2 times 33.2. This ends up being negative 55.3 kilojoules per mole. 304.4 minus 2 times 240.1. This is negative 175.8 joules per mole Kelvin. And so they want us to find it at 298 K. And so if we want to find that delta G, what equation do we use?
Delta H minus temperature delta S.
Minus T delta S. Yep. Right. So a delta G becomes 55,300 negative minus 298 times negative 175.8. So a delta G is a negative 55.178 kilojoules per mole. And then it wants us to find our K. So how can we use our delta G to find our K? What does that one look like for us?
What is it? Negative RT ln K?
Very good. So delta G is equal to negative RT ln K. And so we can plug that in as negative 55,178 joules is negative 8.314. Sorry, joules per mole K. Wrong R. 298 Kelvin, and then ln of K. Now, I did want to mention that the trickiest part about these is just making sure that you remember which R to use and making sure that you stay either in joules or kilojoules. So you just want to keep track of those as you work your way through. But we get ln of K is equal to 22.27. And so then our K becomes something monstrously large. Hold on. Yeah, I think I might have made a mistake somewhere. Let me double check my math on this. Because I think we should be. No, hold on. So we have 55,300 plus 298 times 175.8. Yes, there we go. This shouldn't be, our delta G was too big. This should have been negative 2.9116. That makes way more sense. So 8.314 times 298. So we get 1.175 is equal to our K. And so our K is 3.239. Okay. Sorry, whenever my value is really big or really small, I like to double check my math, make sure I didn't make a silly mistake. Kind of like what I did there. I think I divided my S value by the 1,000 instead of the whole thing by the 1,000. All right. And so we have our K value there. Do you guys have any questions about how we got there?
No, I just always keep forgetting to convert delta H from what, like kilojoules or joules or.
Yeah, that part. It's because, and it's just based on the size of the number, right? Is that delta H is so often given to kilojoules because that's where it like is in that, hundreds to 1,000 range, where in reality, entropy has to be in your joules because it's in the hundreds to the thousands range in joules, right? So that part always has to get scaled, so it does throw things off, for sure. Now for C and D are a lot more like Chem 120 stuff than the Chem 121. So I'm not going to spend too much time talking about them, but it's kind of this idea that, well, if we did it at 308 Kelvin versus 298, what change do we think has kind of happened? And so if you were to write this equation, at 298 Kelvin, right? That would be both of these at 298 Kelvin. We could change it to 308. All that would have to happen is we would have to heat this from 298 to 308. And so that's the CP times our moles of our NO2. And this one would be CP and the moles of our N2O4. And so that's kind of what they're showing you here, is kind of that change, right? Is that our enthalpy between these two, if we were kind of like we're comparing this cycle, is we've needed to add in enough heat to go from 298 to 308, or from 308 to 298. And so we're trying to figure out whether this change is going to be a positive or a negative. So if we compared those two, that the change in the amount of energy needed to heat our reactants, or heat our reactants to the second one versus our products, we spend more energy heating our products than our reactants, then we know that that delta H should be greater at 308 because it requires more energy for us to move those products up, right? Because if we look at that delta H, it should be all of this minus this. So everything kind of stays the same in that first part. So we're really comparing the CP of the N2O4 minus 2 times the CP of the NO2. Right? And so since this is positive, then our delta H is going to be positive or more positive for the 308K. For your entropy, or for doing it whether it's a liquid or a gas, it's doing this similar concept. The only difference is now you have to vaporize them instead. So they're saying that if you had them as a liquid at that same temperature, what would you anticipate? This is a lot more Chem 120 stuff. So I'm not as concerned about it, but if you guys want some more clarification about that, we can go through that in kind of more detail.
I feel good on that part.
Okay. How do you feel, Katie? All right. Looks like we lost her. Okay. So that's kind of that for the thermodynamics part. The interesting about electrolysis is it can both get to your Ks and your free energies, right? Those things are all kind of involved in that process. Right? So a lot of times they just give you your process here, and you want to think about whether this is going to form at your anode or your cathode, right? Now, it gets kind of tricky, anode and cathode, when you get into an electrolysis cell. So let's first think about it this way. When we'll go through this process, is ammonia the product of an oxidation or the product of a reduction? What do you guys think?
Oxidation.
Right? From what? What's being oxidized in the NH3?
Oh, sorry, I was thinking something else, but I see that. It's reduction, right? It's gaining.
It's gaining, right? Because our N is going to a -3 from a 0. Right? So it's going to be a reduction to NH3. And so if we're reducing something, then this is going to happen at our cathode. Right? The oxidation will happen at our anode. So we're going to make that NH3 at our cathode. That's where we're going to capture it from. The one on the anode is going to be our oxygen gas. Now they've given us our delta G's here. And so they want us to find our standard cell potential for this. Now, did they give us all of the delta G's that are inside that equation?
No.
No. So what do we know about nitrogen and oxygen gas, which is why we can still solve for this delta G? What's the free energy for oxygen?
Wouldn't that be 0?
Yep. So 0, and for nitrogen 0, right? Because they are in their natural state. So we don't have to do any type of math to figure that part out. And so now we need to do our products. So 2 times -16.4 minus our reactants. So 3 times -237.1. And so this becomes, our delta G is negative or a positive 678.5 kilojoules per mole. And then we just need to plug that in to find our E cell. So delta G is equal to NF E naught. I've got my negative sign there. Now, how many electrons need to be transferred in our reaction? How many electrons do you think get transferred in this reaction?
It's going to be 3.
So if this was 3, right? Each of these nitrogens is going from 0 to a -3, right? But how many of those nitrogens do we need to convert to make NH3 as it's written?
Oh, so it's going to be 6.
It's going to be 6 because we have to do 2 of them each, right? And so it all depends on how you found your delta G for your reaction. If you use the coefficients that were in front, the 2, the 1.5, the 3, then you have to use the 6. If instead you had found it for 1/2 of this, 1.5 of this, 1 of this, and then 0.75 of that, then you could use 3. But since we just used it how it was balanced, then we have to balance the number of electrons in there. So it should be 6 electrons coming in and 6 electrons being produced. So that gives us delta G is equal to -6. And then what's F?
Faraday's.
Faraday's. 96485 coulombs per mole of electron. And then we have E naught. So this should get turned over into our joule. So 678,500 joules. And then we can basically end up solving all of that for our E naught, which ends up being about -1.17 volts. Okay. Any questions on that part? Okay. So it then asks us whether that should go higher or smaller at lower, or should be larger or smaller at higher temperatures. So what do you think? We know that our delta G is tied in with our E naught. And if we're thinking about temperature changes, we're thinking about how is this equation being influenced by the change in RT. So for this reaction, is our delta S positive or negative?
It'd have to be positive, right?
It should be positive because we have more moles of gas in our product side than our reactant. So we're thinking our delta S is positive. So if delta S is positive, as T increases, what happens to our delta G?
Becomes more negative.
Becomes like smaller. And since our E naught is tied to our delta G, as our delta G becomes smaller, our E naught is also going to become smaller or less negative.
Okay, yeah.
And it's just because they're both proportional to each other. The signage is different, right? So delta G was a positive sign, E naught was a negative, but it doesn't really change their, because they're talking about your magnitude, then they're both going to move closer and closer to zero. Okay. Now, for D, it's saying that the standard reduction of O2 in the acidic solution is 1.23 volts, but they want us to write it in a basic solution. So what do we need to do for a basic solution instead? Can we have these H pluses floating around in there?
No.
No, right? So instead of H pluses, we basically need to put in hydroxides. So what we can do is we can kind of start neutralizing out those H pluses. So if I add in 4 hydroxides over here, that's going to remove those H pluses and that's going to turn them into water. And so then we can remove our waters. And it kind of works out. We have 2, 3, 4 oxygens. We have 4 oxygens. We have 4 hydrogens. We have 4 hydrogens. So we can find that there for our base one. Now, when we want to look for a standard reduction one, I'm going to just use theirs because I actually think it's well written out. We've kind of come up with our new equation here. If we want to look for that new E naught, what we're going to do is we're going to look for that new delta G value for this reaction. Now, we can take our reaction here and we're going to look for its, this is our acidic one, so we can find its delta G's. And we can look at our water ionization to find its delta G. So all that they've done is that they scaled it because there's 4 of them. So their negative RT ln K, they needed to use 4 times, because this should be H plus times OH minus. Each one of those is 1.0 times 10 to the minus 14. Do you have any questions about how they got to delta G's from it?
No.
Yeah, and so once they had their delta G's, they just add them together because that gives us this reaction here. And so once they added them together, then they got their voltage. So when in doubt, when you're looking at like for the reduction reaction or a new potential for something that you don't know, you can always go back through your free energies. And if you can figure out your free energies, then we can kind of back translate them into a potential at that point.
Okay, that makes
Okay.
sense.
They want the reduction of our N2 NH3 in our base solution, and then they want us to calculate that. And so we kind of do the same thing as what we had up here. The only difference is that we're going to add in hydroxides instead of O2. And since we know that O2 can be turned into hydroxide using that 0.4 volts, then we can use that to find our E cell. So our hydroxide reaction, this 0.40 volts, that's going to happen for our, that's going to be our anode process. So if we want to look for our E naught is going to be whatever we had for our nitrogen here. So our, where is our, oh, the 1.17 volts. That's going to be our -1. And then we're going to add to that our 0.4 volts from the basic oxidation of O2 gas. And so that's how we get -1.17 plus 0.40 volts, which gives us -0.77 volts. Do you have any questions about how they figured out our cell potential?
No, that's the one thing I was actually focusing on in this subject, was trying to figure out cell potentials.
Good. That one is like your, so there's like basically 3 big concepts, right? Your cell potentials is one of them. And so just remember that if you set up your anode process or your oxidation, your reduction reactions the correct ways, then you don't have to worry about E cell being E cathode minus E anode, right? You can arrange them in the correct path and just add them together if they're looking for the E cell, and you have your 2 separate half reactions, right? If you want to do it as your cathode minus your anode, that's fine. Just remember, don't flip them, right? So if you flip them, then just add them. If you want to use E cathode minus E anode, then don't flip them, right?
Okay.
So you have your E cells. The other one is getting into your delta G's and your K's from there. Just because it's a important concept for us to carry all the way through. And so I think that that's an important thing, is that your electrochemistry is not off in a realm all by itself. It actually does tie into your spontaneity and your equilibriums. That's a big part about what it's used for. So like pH meters are all about finding your cell potentials because they're tied to your concentrations. So you just want to make sure that you have pretty much this equation right here. Delta G is equal to -RT ln K. And then delta G is equal to -NFE. So these 2 equations right here, right? Those are the 2 big ones. And then the last one is what we're going to get into right now, which is electrolysis. Right? So yeah, those are the big 3 for this kind of chapter. Is, can you calculate an E cell? Can you take an E cell and turn it into your free energy or into your equilibrium constant? And then can you do your electrolysis, right? Those are the big ones. So in either case, what they're trying to say in this one is that, well, we're going to electrolyze ammonia into nitrogen, and we're going to run it for 3,000 seconds at a current of 1.2 amps. And we're going to produce this number of moles of NH3. And so now they want us to look at our yield. So first, let's just figure out how much NH3 we expect it to make. So at 100% yield. So we know that we ran for 3,000 seconds. And then what is the units for an amp? It's 1.20 amps, but what's an amp mean? It's something per second.
I wanted to say like molarity per second, but not.
It's not a molarity per second. It's something called a coulomb, right? So it's amount of charge per second, right? So 1 amp is equal to 1 coulomb per second. And the nice part about the coulomb is 96,485 coulombs is 1 mole of electrons. Okay. So we can use that equation to kind of figure out how many moles of electrons we have. And then we said how many moles of electrons we needed to make 2 moles of our NH3. How many was that? If we're looking back at this equation up here, how many moles of electron did we need to make 2 moles of our NH3?
It was 6, right?
It was 6. Very good. Welcome back.
Sorry, I've been here. I've just been having internet troubles.
Okay. And so from there, we have our moles of our NH3. And so this was what would happen if we had perfect efficiency, which is probably unlikely, but it's a nice world to live in. And so we would have 0.0124 moles of NH3. So how can I take the value that they gave us and turn that into a percent of efficiency? What do we need to do if we want to change that into a percent?
Wouldn't it be what we found or what was produced times 100, right? With the NH3.
So is this one going to be our theoretical or our actual? The value that I just calculated, this is 0.0124.
That's your actual, right?
Mm-hmm. This is our theoretical. Because this is what we calculated based on their inputs. This, the part that they said they produced, so that 1.05 times 10 to the minus 3, this is the actual. But you're right, it should be our actual divided by our theoretical. So we should take the 1.05 times 10 to the minus 3 divided by our 0.0124 times 100%. We get about 8.4%. Any questions on that part? All right. So that's kind of bringing us to the end.